Okay, so today I will start with a new section, that is the numerical integration. And here first of all I will talk about that what is the relationship between summation and the integration, or that how summation is related to the integration. And then under this I will discuss with you the rectangular method, right? And it's a very beautiful method. So first of all let me describe that what is the meaning of integration, simplest meaning of integration. So let me talk about it, that what is the meaning of integration. Suppose we are given a function and say this is the function f of x, and we are asked to find out the integral, okay, from integral of f of x from a to b. A to b is the limit of x, means x is varying from a to b, so it is x-axis, and say it is y-axis or it is f(x)-axis. So it is x-axis and it is f of x-axis. So suppose this is the point A and this is the point B. So if I am asked to find out the integral f of x a to b, right, then what does it mean? It means that we are interested to find out the area under this curve. What is the area under this curve? That's what we are interested to find it out. That's the meaning of it, right? So this is the shaded region. So basically we are interested to find out this area under the curve, right? So that means, what does it mean? It means it is the area of the shaded portion or the shaded region, right? So one thing that once you have the idea of the that how to calculate the integral of the function, then you can calculate exactly that what is the area. But how the idea of integration will came into our mind? So for that let us do one thing, let us draw another diagram and let us try to approximate this area. So suppose we are having a function, it's like this. It's a function, it's a continuous function, right? And say we are interested to find out the integral of f of x from x naught to xn. It is our initial point, say it is x naught and say it is xn. Then this point is, what I did, I divided this region into n small segments, right? So that means what I did, xn minus x naught divided by n, it is the width of each region. So that means this is the x1, this is x2, this is x3, this is xn minus 1, this is xn minus 2, and so on and so on, right? And let me draw perpendicular. And so on, like this, and from here to here. And And if I draw rectangles, say one rectangle I am drawing is this, right? This is one rectangle. Another rectangle I am drawing is this one. Sorry, it's not this, but it is this one. This is another rectangle which I am drawing, and another rectangle is this one, and here another rectangle is this one, then another rectangle is this one. Now what is the area of this particular rectangle? The area of this rectangle is this distance. What is this distance? This distance is f of x1 up to this point, and the separation is what? X naught minus x1 minus x naught is what? It is h, which I have defined here. Equally spaced segments are there and each having width h, right? So multiplied by h, it is the area of this first rectangle. Similarly, this distance is f of x2, so corresponding to it I can estimate the area of this second portion. What is its area? Its area will be f of x2 into h. And similarly, I can estimate the area, this area. What about it? This area is f of x3 into h, and so on. And what is this? Is xn minus 1. This is xn minus 1. So its area will be what? Its area will be f of xn minus 1 into h. And its area is what? Its area, it is f of xn into h. So that means this is a way. So here there is a possibility, depending upon the shape of the curve, either I am underestimating or overestimating the area slightly. ठीक. So this integral is nearly equal to area of these small rectangles, and this area is either underestimated or overestimated. There are two possibilities, either underestimated or overestimated. So that means this is the nearly. And what we can do, we can improve the result by increasing the number of rectangles, right? And another thing which we have to keep in mind, that our result will be improved by increasing the number of rectangles, or in other words I can say that decreasing the width of the rectangle. Width of the rectangle, decreasing the width of the rectangle. That's what we can do. So let us try to look at it mathematically, that how things looks like. So mathematically I can write down this integral I from x naught to xn, and let me call x naught as a and xn as b, because generally we write down integral of fx from a to b. So let us call it as x naught and xn, whatever you want to call. And this area is nearly equal to what? This is h fx1 plus h fx2 plus and so on h fxn. Or because I summed all the all the areas of these small rectangles. So what does it mean? That it is equal to, this is h f of x1 f of x2 plus and so on f of xn, and I can write down it in the form of a summation. it is f of xi. Right, it is f of xi, or I can also write down f of xi into h, and let me call that h is equal to dx I, or simply dx. So I can write down this as f of xi into dx. Now this thing can be estimated as now see, if this is the approximation of this integral, but how this summation can be written in the form of integral, let us have a look at that. So if f of xi dx, it will become integral but when it will become integral when this I varies from 1 to n, where n approaches to infinity and dx approaches to 0. Then there is no error. If I am having an infinite number of rectangles and the width of each rectangle approaches to 0, in that case this summation will become the integration. So this is the idea behind it. So this is the idea of basically integration. N will be infinity, number of segments, number of rectangles, and dx approaches to 0, means width of the rectangle should approaches to 0. So this is the very beautiful method. So this method, or this formula, is known as the rectangular method. So you can use rectangular method on computer to do integration, but in this case the error will be more. So how this can be improved? So this can be improved in another method, and that method is known as trapezoidal rule. So I will talk about the trapezoidal rule in the